All right, here's a pretty simple kinematics equation. Final velocity equals initial velocity plus change in velocity. Now, using the definition of acceleration, which is change in velocity over change in time, I can cross multiply and get this, which is one of the 5 kinematics equations, VF equals VI plus AT. And there it is a little bit differently. This is just saying, instead of saying final velocity, it's saying V of t, which is the velocity at a certain time, is the initial velocity plus AT. And what I have here is an equation in slope-intercept form. So y equals mx plus b. Now for slope-intercept form, this is my y variable, or my vertical axis variable, and this is my horizontal axis variable. So I'm going to plot velocity on the vertical axis versus time on the x-axis, or the horizontal axis, I should say. And from that, the coefficient in front of the horizontal axis variable is the slope, which in the equation you can see that. And then it also makes sense on the graph. Slope is rise over run. The rise of the graph is the change in the velocity. The run of the graph is the change in time. Acceleration is change in velocity over change in time. So the slope here is acceleration. The last variable, the y-intercept, well, that's where the graph's going to start at time equals 0. So that's the starting velocity. Okay, so a quick word about velocity versus acceleration and how that affects speed. So when velocity and acceleration were in the same direction, an object speeds up. When they're in opposite directions, that means the object's going to slow down. So just looking at this here, got this guy right here. I'm going to give him a positive velocity and then a positive acceleration. And he's getting faster, like that. Now I'm going to change his acceleration to be negative. So he sped up. I'm going to change the acceleration from positive to negative. And he slows down. Okay, and he just turned around. Now his velocity is negative and his acceleration is negative. So before he had positive velocity, negative acceleration, slowed down because opposite directions. Now it's negative velocity, negative acceleration, so they're both negative in the same direction. So he should speed up in the negative direction, which he's doing. Okay, so same direction, velocity and acceleration, he speeds up. Now his velocity is pretty negative, going to make the acceleration positive. Now again, acceleration and velocity have opposite signs, so he should slow down, which he does. Okay, and then here's what that looks like on a graph. Okay, example A is going to look at a velocity versus time graph and how to tell whether speed is increasing or decreasing. So the general rule, again, is that if velocity and acceleration are in the same direction, an object speeds up. If they're in opposite direction, the object's going to slow down. Okay, so there's 5 segments here, A, B, C, D, and E. And for this, the slope of the graph is acceleration. So for segment A, it's above the x-axis, so it's positive velocity. And then also, it's sloping upwards, so it's positive acceleration. So from that, I know at part A, the object is speeding up. Okay. B, it's not stopped at B, it's a horizontal line. That means it's moving, but it's not accelerating, so it has constant velocity or constant speed. Okay, moving on to C. So C is still positive. The graph's above the horizontal axis there, so it's positive velocity, but the slope, it's sloping downwards, so that means there's a negative slope, therefore a negative acceleration. So velocity and acceleration are in opposite directions, so that means here the object is slowing down. Okay. Then on to D, now it's below the horizontal axis, so there is a negative velocity and a negative acceleration. Now, negative acceleration does not mean deceleration, doesn't mean slowing down here, because let's say this is like -5. and its acceleration is still negative. It's going from like -10. So the velocity is decreasing, but speed, which is its absolute value, is increasing. So I have a negative acceleration. They're in the same direction. So that means it's going to speed up here. And then last one, E. E is still below the horizontal axis. So the velocity is negative, but now it's sloping upwards. It's going from, again, just for example of a number, -10 to 0. So the velocity on this part is increasing. It's going from a negative number approaching 0, but its absolute value, which is speed, is decreasing. So it's slowing down here. Here's another way to think about example A for finding whether an object is speeding up or slowing down on a graph. So here the object's speeding up and it's moving away from the time axis. Here the object's slowing down and it's moving towards the time axis. So in general, if velocity and acceleration are positive, that means the object's moving away from the time axis. If they're both negative, it's also moving away from the time axis. And if they're opposite signs, that means it's approaching 0. So if the graph is approaching the horizontal axis, then it's slowing down. Okay, so slope of a velocity versus time graph can give acceleration. That's not the only thing that can be calculated from a velocity versus time graph. You can also find the displacement. So for that, here are two velocity graphs. They're both physics 1 level because this is constant velocity. This is constant acceleration. So on the left, I have a rectangle. On the right, I have a triangle. These are the formulas for the displacements from kinematics, which are both just saying basically average velocity times time. I'm going to look at the left graph here. And I'm going to form a rectangle with the graph. And this rectangle is going to have a height equal to what the velocity is. So this is the velocity axis. So whatever the velocity is going to be the height of the graph. Then the width of the graph is the total time that the graph is looking at. So that's a rectangle with dimensions of velocity times time. So the area of that graph is velocity times time, which is also equal to the displacement. Now it's a bit more complicated if the graph is sloped because there's an acceleration. But for simplicity, I'm going to say that VI is 0. And if I do that, I have a triangle. So I have height of VF because VI was 0. The base is time. Area of a triangle is 1/2 base times height. And that's also equal to, again, the displacement. So in general, if you have a velocity versus time graph, you can find what's called the area under the graph, and that's going to give displacement. Now, area under the graph basically means whatever the graph, like the function is, you're taking the area between that function and the horizontal axis. And for displacement, whether it's above the horizontal axis or below does matter. So here, this is positive area, so it's positive displacement. Down here, this triangle is negative area, so it's negative displacement. All right, so one more example looking at a velocity versus time graph, and this will get into asking about displacement later on. So this is the velocity of a thing. It starts positive, goes to 0, then goes negative. So question A, was the thing released from rest? So obviously the answer is no, because it starts at 10. So the graph was not released from rest. And the way to know, if a velocity versus time graph is released from rest, it'll start at the origin. It'll pass through 0, 0. So if a velocity graph passes through the origin, that means it starts at rest. Part B, find the speed at 8 seconds. So 8 seconds is going to be right here. The vertical axis here increments by 2, and it's negative. So the velocity is -6. And again, speed's the absolute value of velocity, so the speed here is 6. And when does it change directions? So for a velocity versus time graph, it's going to change directions when it crosses the horizontal axis. For a position graph, it changes directions when the graph literally switches directions. But this is a velocity graph, so when it's when it passes through velocity equals 0, which is the horizontal axis. All right, here's the math on this question. Part D, find the acceleration at 8 seconds. So 8 seconds is going to be right here. Slope is acceleration. This is a straight line. So the slope is constant. So the acceleration is constant. The slope's also negative. So the acceleration is negative. And to find it along this line, I can just take 2 endpoints. I'll take this one and this one. So this is 0, 10. This point here is 10, -10. So to find the acceleration, I just find the slope. So acceleration equals slope. And that's going to be rise over run. So it's going to be on top -10, -10. And then change in time. So it's 10 minus 0 on the bottom here. So what I have is -20 over +10. So the acceleration, which is the slope, is -2. Okay. So the displacement on a velocity versus time graph is the area under the curve. That means the area between the x-axis and the graph. So this is asking to find the displacement for the entire motion. I'm going to do this in steps because there's sort of, I guess there's 2 shapes here. I don't want to work with a trapezoid. So I'm going to say there's 3 shapes, which is this triangle here, which is positive area, this triangle here, which is negative area, and then this rectangle, which is also negative area. So I'm going to go through step by step and find the areas there. So for the first one, it's a triangle. The dimensions are height 10, base 5. So I'll call this area 1, area 2, and area 3. So the area of part 1, I'll call this displacement of part 1, is going to be area of a triangle 1/2 base times height. And that's going to be positive 1/2 times 10 times 5. So 5 times 5 is 25. So that means after 5 seconds, the object being graphed here has gone in the positive direction for 25 meters. But they're going to have stopped because here at time equals 5 seconds, the object's going to stop and then turn around. So it gained positive displacement, but now it's turned around. So it's going to lose displacement. It's going to go back to 0. And I have this triangle over here. This is 5. This is, again, 10. So area 2, displacement 2 here is going to be 1/5, or 1/2, times 5. And then times -10, because the height is -10. And that's going to be -25 meters. And what that means, since it has, at this point, after points 1 and 2, its total displacement to time equals 10 seconds is 0. That means that it's back where it started. So the motion so far, I have an object, it moved, and then went back to where it started. Now the graph does continue. So what happens here, it moved, returned to its starting position. Now it's going to keep going in the negative direction. So to find the final displacement here, I'll look at region 3, that rectangle there. So I have delta x 3, and this is a rectangle. The units are going to be in the x direction 5 and the y direction 10. Area of a rectangle is just base times height. So I have 5, and then it's negative, so -10. and that's going to be negative 50. So to find the total displacement, I just add up the 3. And that's going to be negative 50, which means what the object did, it started here, went over here a little bit, turned around, came back, and then went in the negative direction. Now, just a note, if I ignore the negative when taking the area, so the area under the graph, which is between the graph and the horizontal axis, if you include negatives, that gives you displacements. But if I just wanted to find distance, I could say for region 1, the area is 25. Region 2, again, distance versus displacement. Displacement is a vector. Distance is a scalar, so the sign doesn't matter. Part 2, it's 25. And then for region 3, it's 50. So the distance traveled here is 25 plus 25 is 50, which is 100. That's the distance, but the displacement is negative 50. And that's velocity versus time graphs.